All right, happy Thursday. How's everyone doing? Great. Nice to see all of you. We have a real banger today. Uh, we're going to cover the one more extension of the general linear model. But I forgot to show you something from last class. My weekly picture of Maxine from the weekend. This is us. We were. How many of you have been to Dad's Dog and Burger? It's like in Bloomfield. Nice. So this is from Dad's Dog and Burger. They just opened up like this fall. We went there and had a cute little time. Max was hungry, as were we. And I just thought this was the funniest thing. I have a video, I'm not going to show it to you, but it's a video of me laughing for literally a minute sitting there. She was just sprawled out like a snow angel. And I would just like move her around the table, and she just like didn't move her body. It's the funniest thing. Anyway, so this is from last class. I didn't show this to you for some reason. And then, yeah, for this class, I just took a selfie this morning. So, cute little thing in our house. Looking forward to seeing her tonight. Okay, y'all feeling good? Well, it's nice to see those of you who made it through the rain and on the pre-Halloween Thursday, right after a mini exam. So, respect all of you for being here, doing your jobs. It's your job to be here. This is not great, but we'll live with it for today. Okay, so we have a big one for today. You'll remember, a couple of housekeeping items before we get in. Homework 3.5 is posted. So I just posted that a couple minutes ago. It's not due on Friday. I think it would be so rude of me to give you homework due in like 24 hours. So I'm not doing that, but you can find the homework. It's posted here. This is really just on t-tests. So I ask you to do it with a t-test and with a general linear model. So you'll be using these tools in the univariate environment in homework 3.5. So that's actually, it says Friday, but that should actually say Tuesday. So if you click on this, it's Tuesday, November 4th. And as always, if you want an extension, you can ask for one, and I'll maybe give you a day. But that should be plenty of time to get it done. And then I've been looking through the mini exams, and I'm generally very pleased with how that went. You can generally expect them to be back roughly in a week. Sometimes it's a little bit longer, like a day or two, but a week is kind of the main timeline. All right, so that's the housekeeping. Sorry for not giving you a Maxine picture last class. That's like unacceptable. Okay, so we're doing a big one today. This is one of the big topics. I think after today, you should be in the ballpark of starting to think about your final projects. So we're going to talk through what we're doing today, and then next class, I'm going to give you a little bit more information on your final projects and what to expect, and then some ideas. So we'll do that next class, but you'll remember what we did last class. The very end of part 3. This was just the very simplest general linear model, which you've seen before as a t-test, a one-sample t-test. We walked through all of part 3, and the big idea there that I've said maybe 15 times now. When we don't know the population parameters, what do? Well, thankfully, we have the central limit theorem, which tells us the sampling distribution of the sampling parameters, which in part 3 was the sample mean. Then we talked about how we could perform t-tests, and then we started talking about linear equations. So we call, this is just a linear equation. We draw a line through our data. The y is the outcome variable, x is the predictor variable. And then, as we'll talk about in part 5, we can extend this into more than like x and y, but we can have multiple x's. Okay, how do we choose the line itself? Well, we try to minimize the wrongness of the model And the way we define the wrongness of the model is with the mean squared error. So we look at how far the model is from any data point. So it's the predicted value of the model, and then we look at the data point. Turns out this is very similar to the variance. The intercept-only model is the simplest version of the GLM. It's essentially just trying to predict the values, the y values, using the mean only. We call x the data, we call b the model, in this case, and e, the epsilon, is the error in green. And this is what it looks like. So the thing the model is doing is trying to pick where the vertical intercept is so that we minimize the wrongness of the model. And the way we did this is by finding the lowest point. This is just what the mean squared error looks like, and we can pick it. We can pick the model parameter by to minimize the mean squared error. So we just pick it at the bottom point, which happens to look exactly like the mean. So the model we draw is simply a line going through the vertical intercept at its mean. And then we talked about the sampling error of the GLM. So whenever we take a sample, what we're doing is drawing a bunch of observations from our underlying population distribution, and then we plot the sample means. So whenever we go through and we estimate these models by picking the line that minimizes the mean squared error, we get sampling variation not just in the sampling means, but in the model parameter itself. So the important part here was we went from thinking just about the sample means to thinking about the parameters of our statistical model. So each time we take a new sample, the model itself will move around. And you told me when we plot the distribution of each of these sample parameters, B, it looks like a normal distribution. This is a mistake in the slides. This should say normal. But whenever we run through and we collect a bunch of samples and we plot the sample means and the intercept parameters, it looks like the familiar distributions that we've been working with hypothesis testing. So this was the big idea here, is we can actually think about the model parameters in the same environment that we've been thinking about hypothesis tests. So then we walked through this whole sequence where we talked about how, mathematically it's identical to center the sampling distribution on the sample mean instead of the true mean. We talked about how this is mathematically identical with confidence intervals, and we did that whole simulation at the beginning of part 3. Okay, so then we can go through and ask different questions, different null hypotheses, making claims about our model parameter B. So what we did, the standard approach here is we recenter the sampling distribution on our null hypothesis. And like we've talked about, it doesn't really, mathematically, it's identical to think of them, the sampling distribution, either on the sample mean or on our null hypothesis. The p-values we construct are identical. So we're just going to jump it over and then find the area in the tails more extreme than our observed sample mean. And this is how we've talked about p-values. This is the probability under the null hypothesis of seeing something as extreme as what we do. And remember, this is like exactly the same approach as we took with hypothesis testing, except we're making claims about the model parameter and not just the sample mean. Turns out these things are equal here, but as we'll get into later in class, we can actually make larger claims. So we can talk about different model parameters, like a slope. Okay, so this was our intercept model, and we talked about the mean beta 0, minimizing the sum of squared errors, the mean squared error, and then the probability of the data given the null hypothesis. And the reason, this is the amazing thing, right? The reason we can do this without observing the population parameters, like we don't need to know the population mean or the standard error of the population. We can do this because of the central limit theorem without making big assumptions on our data. This is amazing. Okay. So then we claim that our best guess of the true mean is our sample. So that would be beta 0. Okay, so this is the simplest version of the larger regression model, which is what we're doing today. So this is all review from last class, building up these ideas of making claims about the parameters of our statistical models using the same approach as we've been doing in part 3. Okay, any questions about that? Big review from last time? Feeling good? Okay, so I have a couple of questions for you today, and then we're going to get into exercise 4.1, where we're actually going to be running some statistical models. So I just posted part 4, so you can take a look at this. So what we're doing today is talking about numerical predictors. So with all of that sort of the very simplest general linear model as a bit of background, what we're going to do today is think about relationships between variables. So this is the starting picture. You all have told me you don't want to keep talking about Starbucks, which is a little sad to me. So instead we're going to talk about wait times. So we talked about, like I sent a bunch of people out to restaurants and sampled their wait time in the morning and then compared it to the same person at the same restaurant, but in the afternoon. So we had 2 different wait times, and that was the last example we talked about, which allowed us to run a t-test. And we walked through this in exercise 3.5. So we introduced this idea of actually running these t-tests on this weight difference data set. And we walked through this. I added a little bit extra here with some visualizations. So take a look at that. But nothing fundamentally has really changed from what we were doing last time. Last time we were comparing wait times in the morning to the wait times in the afternoon. What we're doing today is instead of comparing discrete times, right, like changes between morning and afternoon, we're going to just look at wait times throughout the day. So that looks like this. And you remember I told you I actually made this data set up. This one is also made up to look pretty on a screen. But the exercise for today, we're actually going to use real world data on happiness and GDP in countries throughout the world in 2024. So that's where we're going, but I just have some nice little contrived data sets for you today. Okay, so this is a question we might have. Instead of asking, is there a difference in wait times if you go in the morning or the afternoon, we could just ask, what are the wait times throughout the day? And are people waiting longer in the afternoon? Or like, are people waiting longer as the day goes on? And you can probably tell from this picture, it looks like there's longer wait times as the day progresses. So as the restaurant or Starbucks location stays open later, people are waiting longer. Okay, and what we did in part 3 is we built this statistical model to make claims about the average wait time. And this was the model we built. So this is just the intercept model. So looking at the estimate of the average wait time without any slope involved. But you've already told me that most of you have already worked with regressions, adding a slope parameter. And in general, when we're in economics, we don't generally make a lot of we don't ask a lot of questions about vertical intercepts. Like, it's not really a big thing that we do. It's not never done, but it's not the most common kind of thing we do. In general, we like to look at relationships between variables. So what we're going to do is actually compare 2 different models. So the one we've just worked with model 1, the intercept-only model. And then we're going to compare this to the more general model, the beginnings of thinking about slopes. This is the simplest kind of model we can deal with when thinking about slopes. And this is the one I mentioned at the beginning of last class, that we made a simplification to work with the intercept only. Okay, so what we're going to do is add a slope. First question for you today, turn to your neighbor, tell them a fun thing you're going to do this weekend. It's Halloween. Or maybe tell, do you all have Halloween costumes? I actually don't yet. But Maxine has one. Maxine's going to be a rubber ducky. And I will have pictures for you on Tuesday. So tell your neighbor your Halloween costume, and then tell them whether you think the second model will have a higher or a lower mean squared error than the first model. Take about a minute here. Just say hi.
Breaking news.
What was the going besides the talking about Halloween costume?
Yeah, so the second question is, does model 1 or model 2 have a higher or lower mean squared error? Like, is model 2 better? Okay, someone tell me, is model 1 or model 2 going to have a higher, which model has a lower mean squared error? Model 1 or model 2? Alexis? Model 2. And why, someone can confirm Alexis's intuition here. Why is model 2 going to have a lower mean squared error? Someone other than Alexis. Negative 10 lecture points. Yeah, Hannah. Yeah, so if we add a slope, you can see that there looks to be a true slope here. Like, the raw data looks like it's maybe increasing in minutes after open. Because there's this true slope within the data, if we draw a line through the middle of the data, we can we'll probably have a better fit, a lower mistake, a lower mean squared error. So let me just put this picture up here, and I think this confirms the intuition here. When we have a slope, we can sort of fit the model better to the underlying data, and so the mistake of the model is smaller. And you'll remember, the way we've been measuring this sort of idea of model mistake is using the mean squared error, the wrongness of the model. Okay, very nice. Any questions here? So this is some of the intuition for what we're about to do. We're going to think about adding a slope, and then think about what that slope represents. And we're going to do this intuitively. There's a lot of background work, and if you're interested in these kinds of things, you can take entire classes. Econometrics, it's a great field. If you have more interest in it, that's a field for you. But essentially, adding this slope generally will improve the model fit. So the mean squared error will go down, the wrongness of the model. And this will be true when there's a true relationship. So when the population actually has a relationship in the data generating process. In this model, when we add a slope parameter, the intercept is no longer the mean. So when we were dealing with just the intercept model, the intercept was exactly the mean. And so we talked about the distribution of sample means, which was identical to the distribution of intercept parameters. But that's not generally true here. We'll talk more about what this vertical intercept means. But when we're thinking about adding a slope, we want to, we'll spend a second just thinking through what we're doing when we minimize the mean squared errors in this context with a slope. So second question for you today, turn to your neighbor, tell them which model looks just visually like it would be the best fit, the minimum wrongness or the minimum mean squared error. Take like 30 seconds here. Okay, so I made a mistake on these slides. I gave you the mean squared error, so this question is not very interesting. But if you didn't see the mean squared error written on the figure, someone tell me which model is the lowest mean squared error? Simple question because I've given it to you. But then tell me why. Yeah, Sophia? Oh, I'm sorry. Yeah. Yeah, so it's model C, and the reason you can see this, I've listed some of the residuals, some of the errors, and you can see they're generally smallest for model C. With model A, it's like there are lots of, the model is larger than all of the data for these points late in the day. And that's just, it gives you error for each of them when you could just draw the line through the middle. So generally what we're trying to do here is draw the line through the middle of the data at every data point, or at every x value that we have data for. So you can see the model C minimizes the error. Okay, any questions here? So we have a very similar idea to fitting models when we have slope parameters. It's a very similar idea to what we did talking about intercepts only. What we're trying to do is get it as close to the middle of the data as possible. And it turns out if we have data that looks like this, the model is going to give us sort of an average prediction at every point on the horizontal axis. We're going to talk about when and why this is true next class when we talk about the assumptions that go into this model. So this is the sort of idea with minimizing mean squared error. And it looks very similar to the figure we had from last class. So this is model C, and then we're just trying to pick the line so that the slope is at the bottom of the mean squared error. So you'll remember, we don't do calculus in this class, but if you like calculus, essentially this is a minimization problem. You can actually take derivatives of these functions and perform minimization there. So if you love that stuff, that's available to you in econometrics, but we don't do that here. Okay, any questions? So the conclusion here, or the way we generally interpret these things, the slope parameters, beta 1, is very similar to how we interpret the intercept parameters. This beta 1 generally gives us sort of this idea of a best guess of a relationship between two variables, x and y. So this is like the closest we have to a guess of the population, even though we never observe the population. But my question to you, maybe third question, if the true slope is 0, is it possible, like if the population slope is 0, is it possible that we could see this slope simply due to sampling error? We're going to take like a minute here. I want you to turn to your neighbor and try to answer this question. And then I'm going to ask you for some intuition for whether we could be seeing this simply due to sampling error. And apologies, Alexis, I meant to give you 10 lecture points instead of taking 10 away. I should take 10 away from me for including the mean squared error on the last slide. Okay, so I'm going to ask you for your answer in that minute. Is it possible for us to see this simply due to random variation, random sampling variation?
Looking at that, I would definitely say it hasn't. So it's not correlation isn't super strong just by adding it up. But there's definitely a positive relationship. And I feel like it would be very plausible to be apparent just from sampling error if the true slope is 0. So I think it's a super thing.
Okay, bit of a distraction. Now, someone tell me, is it possible for us to see this data if the true slope is 0? Like, our sample has a slope to it, right? And we fitted the model, looks like there's a slope. Our best guess is that there is a slope. But is it possible for there to actually not be a slope in the population? Like, obviously there's a slope in our data, but in the population, could it be that there is no slope? Jay. Okay. Okay. So Jay's saying it definitely, like, there are situations where X and Y are independent from each other, and so there would just be like random noise behind the scenes. Someone else, what are some other ideas here? Darren?
I guess just the nature of random sampling, slope doesn't always have to be the same each time. Let's say like there are extremities that'll eventually pull the slope up, that'll change. Like, this is why at which the slope is 0.
Yeah. So just like we had last time, do you remember that figure? I think it was maybe 2 classes ago. I plotted a bunch of samples and each of their sample means. Every time we take a new sample, the data looks slightly different. The sample mean will be slightly different, and the sample slope will be slightly different. So just as Darren and Jay are saying, we have sampling error, not just in our sample means, but in our sample slopes. So now, if I were to ask the question, is it possible for us to see a positive slope, but for the true population slope to be 0? Do you think it's possible? Yeah, Luke.
I would say it's possible, but not necessarily likely.
Okay.
Because as we're seeing there, like Brian said, like, I'm sure if you did this for more and more samples, you would see that most of the scatter plots for the samples exhibit positive slope.
Okay.
So, of course, it's a statistical possibility, but I don't know. I think looking at the previous slide, in Maldives, I'm pretty certain that there's an increasing trend. But
Okay.
the population could.
So what Luke is saying is, it's definitely a possibility. It's definitely a possibility that the true relationship between X and Y could be zero. Could be no relationship, a horizontal line. But it's intuitively, it feels unlikely. And that's exactly the right idea. It's possible, we can't rule it out, but it doesn't seem to be that likely. Anyone have an idea what would happen to the distribution of beta 1s? So if I just took all of these samples, I fitted the models for each one of the samples, and then I plotted the beta 1s, the slope parameters. I want you to turn to your neighbor, tell them what distribution you would expect from this histogram. So I plot a histogram of all of the beta 1s. What does that look like? Take about a minute here.
Because just look at these, for example, when you see a lot more positive as you see so you're going to have less than 2. Because of that, it's going to be more oriented. So you're going to have 0 at the center. I would say that there's
You all have wild guesses. No, okay.
Let's see it.
Yeah, I'm looking for wild speculation.
Because the slope isn't.
It's the main thing here.
It's not like.
When I wrote these slides, I came in expecting that at least a few of you would get this right. I'm going to run 1,000 observations and plot the histogram of the slope parameters, right? Like I've listed the slopes for each one of these samples. Each one is slightly different, as you can see. Some of them are even negative. And I'm gonna plot 1,000 of these with a histogram. Anyone have a guess for what that distribution will look like? Alexis. Alexis is saying a normal distribution. How many of you expected, would have, if asked, said a normal distribution? Hands up. Okay, so yeah, some good wild speculation on the side. Look at this. Can I show you the distribution of the sample slopes? What is this telling us? Can I just pause in amazement of this figure? Is this not amazing? This is told to us by the central limit theorem. The central limit theorem does not make just claims about the sample mean, but it makes claims about other sample parameters as well, like this one. This is a bunch of slopes. This is the distribution of the slope parameters when I run 1,000 samples. This is one of the pictures I want you to have in your head when we start working with general linear models. I want you to think about this thing. I want you to think about the distribution of the sample slopes for all of the other samples that we didn't run. We only observe one. But what we're doing is sampling from some underlying distribution that's centered on the truth. Any questions about this? Are you not amused? I am. I am deeply amused by this. This is not just interesting, but it's powerful. The reason it's powerful is because we can then make claims using the central limit theorem without knowing the true population slope, we can make claims about the population slope, just like Luke did. It looks like, in general, we're very far away from zero. So we're going to make claims about the slope being different from zero. And if you're thinking about p-values, like looking at this, we should be able to construct p-values about the slope parameter, not just the mean, the intercept parameter, the mean. We can make claims about the slope parameter. Okay. I should have included an emoji here. Do you remember that mind blown emoji from the central limit theorem? This is one of those cases too. This means, just like we did with the normal distribution into the t distribution, when we don't know the standard error of the slope parameters, we can use the standard error of our sample slope to give us a t distribution on the slope parameters. So we're going to go from a normal distribution, which is the truth, to one where we don't know the standard deviation. Okay, so we don't observe all these other samples, right? The only one we see is the one that we drew. So we can center the sampling distribution that we know what it is, and just like before, we can then, it's mathematically identical to move it to be centered on the null hypothesis. And then we're going to make claims under the null hypothesis. We have the sampling distribution centered on the null hypothesis. We're going to ask how likely is it that we're seeing a slope as steep as the one we're seeing if the true slope is zero. So in some sense, Luke was saying it's unlikely that we're going to see the thing that we do if it were truly zero. And what we're going to do is put a number on it. And the reason, the way we can put a number on it is because we know the sampling distribution from the central limit theorem. Okay. Remember, like 4 weeks ago, we were talking about data cleaning? Remember how boring that was? We had to do it, but this is the fun stuff. Okay, so this is the picture. You all have this in your heads. We have our sample slope, which is we drew a bunch of data. We're plotting the slope of our x and y. We have our default null, which is going to be that there is no relationship between these variables, which is a much more interesting null hypothesis than we're doing when we do single variable t-tests, right? Like you could ask, is the mean different from any number, like 10? But that's not so interesting. Like, how do you pick the null hypothesis? When we're talking about slopes, it's very easy to pick a null hypothesis. The default null hypothesis is that there is no slope, that there is no relationship. So when we run these things, we generally ask whether there is actually a relationship by checking the default null, which is beta 1 is equal to 0. We're going to spend a lot of time with this. So we have our sample, we have our default null, and then we have to look on the other side of the default null for the equally extreme value. And then all we're going to do is find the area in the tail. So we're saying we can find the probability of seeing something as extreme as what we do if the truth actually is no slope. If there is no relationship between the variables, what's the probability we see a slope like we do? We can quantify it with a p-value, just like we did in hypothesis testing. Is this not amazing? Have you heard this said before? Like, raise your hands if you've seen regression. And raise your hands if you've seen it said this way. Luke is the only one. Okay. This is how we interpret results from regressions. We can fit a line of best fit, but it's making claims about a true underlying probability. Like the probability of us seeing something this extreme if there is no relationship, which allows us to make claims about the truth. All right. And these are just some of the different things that I've said verbally. The last one is essentially a small p-value. You've probably seen this before. A small p-value is strong evidence that it's different from zero, right? Like that's how we interpret a p-value. If you get a small p-value, that means we're very far, this thing is very far away from zero, which is strong evidence that that the truth is not zero, a slope of zero, that there is a relationship. Okay, so if there's any picture I want you to have in your heads leaving this class, it's this one. Let me just talk you through. I showed you a figure of a bunch of samples from before. So remember we had this thing, a bunch of different samples, each one has a separate slope. All I've done is put all of those slopes on one figure. And what I'm showing you here, we have many different possible slopes drawn from the underlying sample distribution according to the null hypothesis. So if the null hypothesis were true, when we drew a bunch of slopes, we would see slopes that looked like the ones in gray. And I drew, I think, 50 to make this figure. What we actually see is the red one. So the underlying data behind the scenes, and then the model through the data in red. If I were to just randomly pick one of the gray lines, what's the probability I would get something as extreme as the one we do? Like how many of the gray lines are as steep as the red one? Like very few. So if we were just randomly select slopes drawn from the null distribution, it would be very unusual for us to see what we see. This is equivalent to the p-value, the hypothesis testing approach on the slopes that we've done, that we just constructed. Okay, so I don't know if you understand this figure or if this is informative. Do you like this figure? It's all right. It's a little confusing. But the main idea is that it would be very unusual for us to see a slope as extreme as this under the null hypothesis, which is exactly this picture. So these are saying the same thing. All right. So this is all fun and exciting. But to really, truly get this idea, I think it's better to actually run some models. No? Negative 10 lecture points. Okay, so how likely does it look like this slope was drawn from the null slopes? Very unlikely. That's the answer. And the p-value is this probability of seeing a slope like this, given that these are the slopes we can choose from. Okay, so we're going to hop over to exercise 4.1. Other than Luke, do y'all like the exercises?
Yeah, that's cool because it sort of looks like our studio code.
Except it's better than RStudio because it's Python. Okay, so yeah, raging debate in the field at the moment. So we're going to hop over to exercise 4.1. So you can click on the notebook. Let me show you the data we're going to work with. So you can click on the source here. This is just the World Happiness Report, which goes around, apparently it's based on the Gallup World Poll, but it goes around the world and asks, like, samples from different countries and asks like a bunch of measures of happiness around the world. And then this is compiled every year, and then there's a world average, a country average that's published every year. So what we're going to do is look at the World Happiness Report and then compare that to GDP per capita. So how much is the country making on average per person? So this is the data, and you can download the data set here if you want, but we're not going to do this in Excel, so no need to put this on your computer. You can click on the notebook. Okay, so y'all excited to see if richer countries are happier? What's your null hypothesis? Do you think there's a relationship between money and, or GDP per capita and happiness? Maybe tell your neighbor an answer and then a null hypothesis and then maybe an explanation. Like why would your null hypothesis be true?
I mean, that's what you'd say to always, regardless of your opinion, because the knowledge it's alternatives always not even if you want to say. Yeah.
Okay, so once you have a null hypothesis in your head and maybe some sort of theory for why your null hypothesis might be true, I want you to use the code I've given you and check. You can check the relationship between the log of GDP per capita and the happiness score. So you can just run the first cell, and then we're going to do what we call exploratory data analysis, what we did in parts 1 and 2. So we're going to try to explore the data. What I've done here, I've loaded the data set. I've done a log transformation. You remember that from like part 1? So I've just done a log transformation on GDP per capita. We're going to talk about why we do this a little bit later. And then I've just filtered for the most recent year. So I run this and I get a data set that looks like this. All right. So let's take a second here. There's some code in the slides, but I want you to not use the code at first. I want you to try to think about a visualization you would use to visualize a numerical variable, which is our main GDP variable, log GDP per capita, and life evaluation, which is the measure of happiness that we're going to use. How would you visualize those two variables against each other to sort of check your null hypothesis, to check whether there's a relationship here or not? We'll take maybe 2 minutes here. If you get stuck, you can use the code in the slides, but try to do it without.
Well, I guess I was thinking, because then we have to check up the plot there, so just to see the distribution. But both could work because it's numerical. We should do a pie chart.
Pie chart is definitely the right choice.
Did I get my lecture points?
Yeah, that actually would give you 100 lecture points.
Let's
a very,
go.
very wrong answer. Look how far we've come from class 1 with pie charts.
Haven't spoken for weeks.
Okay, someone want to tell me what you did? Ruby. Okay. 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 Log GDP per cap. Life evaluation. Is that what you did? Okay. Okay, so plt.show. You actually don't need this in a notebook, but you can include it if you like. It doesn't break anything, it's just not needed. What is needed is correct spelling. Ten lecture points. Actually, aren't lecture points are bad? So you should be in the in negative values. So yeah, negative 10 lecture points. So now you can't trade them with your friends, sadly. Okay, so this is how I would set it up too. This is almost exactly the code I have in the slides. Oh, I guess I don't have a figure in the slides. My bad. But yeah, this is a nice figure. We have two variables, and we're trying to visualize a relationship between them. Some of you may have started with a histogram, which is fine. So you could do sns.histplot, and then you could plot either of the values. But I think for our purposes at the moment, this is enough. How does this feel intuitive? Like that this measure of happiness would be increasing? I mean, for me personally, I would have thought it would sort of level out at a certain level. And that may be true. Like this is us up here at the very top of the GDP per capita. It might actually be this one. Like we're not the happiest country in the world, but we definitely have, oh, this is us. Or one of these. There's some oil producing countries that may have a higher GDP than us per capita, but we're up here somewhere. Okay, so yeah, generally happiness seems to be increasing with wealth. So when your country makes more money, produces more, you generally seem to make more, to be happier. Okay, so what is it that we want to do? Well, if we've done the visualization correctly, the model should be very obvious. All we want to do is draw a line through our data. We're going to draw a line so that it minimizes the mean squared error. So what we're doing here, we're actually going to build a statistical model of this relationship. And we're going to test whether this could be due to chance alone. Whether it could truly be zero. Like what's the probability that we see something as extreme as we do if the truth is zero? So what we're going to do first is build this model. So you can see this in the slides. We're going to build a model with a y variable, an intercept term, and then one slope term. And let me just talk you through what we're seeing here. The intercept term is going to come by default with this model. So you don't actually have to specify it if you're including slope parameters. So we're going to, if we include a slope, we're going to by default include an intercept term. So what we want is our y variable to be the variable on the vertical axis. I want to know so the outcome variable being happiness. And then I want to know the predictor variable, like can we predict happiness using GDP per capita? And the way we write this model looks like this in code. We have our y variable, and then this squiggly sign, which tells us that we're on the predictor side, and then we have one predictor variable. And then I've included some other things here just to make the output look nice. So you can copy this and hop back over to the notebook. And I'm going to run this. And then you're going to tell me some of the things you're seeing. Actually, you're going to try to interpret some of the things you're seeing before we do it in the slides. So you're going to turn to your neighbor and try to make some claims about these things. Let me just walk you through generally what we're seeing, though. When I run this model, I'm getting one row for the intercept term. I have the coefficient, so this is the predicted value of the beta. So this is the value for b, or the beta 0. I have the standard error. So on your mini exam, you computed standard errors. Here, the computer is just going to do it for you. This is the standard error of the sampling distribution around the sample mean, or the sample parameter, b. So this is the standard error of that t distribution around the sample. We have a t-score, which is not something we're going to work with. You probably spent a lot of time with this in your stats class. We're not going to do that here. We have a p-value, which tells us the probability of seeing an intercept term this far from 0, if 0 is the true intercept. And then we have a 95% confidence interval. And you can check whether the 95% confidence interval contains 0, if you wish to think about it that way. So that's all for the intercept term. I want you to turn to your neighbor. So this second row is for the beta 1 term. And we interpret everything with beta 1 identically to beta 0. It's just now we interpret it as a slope. This is the estimated value for the slope parameter. This is the standard error of the beta 1s. So the distribution of beta 1s, just like I showed you in the slides, the spread of that distribution is given to us by the standard error. The t distribution, the p-value, and then the 95% confidence interval. I want you to look at this number, turn to your neighbor, and tell your neighbor what this means. Take a crack at this. You don't have to get this right. Wild speculations are strongly encouraged. And then one of you will try to answer, we'll try to interpret what this p-value means together.
Because the p-values probably that we give value as extreme as 1 or 5 or more extreme, given assuming that all is true, but that probability is 0%. I'm going to say that I'm getting redemption.
Okay, someone want to interpret this p-value? What is this telling us? It doesn't have to be a complete answer or even correct, but how do we talk about this p-value? I see Luke's hand and I see Alexis's hand. Darren.
The p-value of 0 means like there's either 0 or smaller than the 3 decimal points chance
Yeah.
of seeing that result if it was completely
Yeah.
that sample.
Yeah. So this is actually said very well. So the probability of seeing something as extreme as what we do in the slope, under the assumption that there is no actual slope in the data. And remember what's going on here. The reason we can make claims about the distance, the probability of distance between 0 and what we're seeing, is because we have the central limit theorem telling us the sampling distribution. We're not making any assumptions about the underlying population. So this is, I would say, very unlikely for us to see something like what we do, given the null hypothesis, which, as I said before, the default null when we run the general linear model is for there to be, the parameter is 0. So whatever the parameter is, the intercept is 0, the slope is 0. That's the default null. Let's see. Ruby, you had an answer?
Oh, just similar to Terrence.
Okay, same idea.
Yeah, like 0% chance of seeing close values, but given that the null is true.
That's right. That second part is actually very important. We're centering the sampling distribution on 0. And then we find the area in the tails. That's the picture I want you to have in your head when we think about these p-values. This is the most important part of interpreting our results, is the understanding what the p-value is telling us. The last parts here, there's the t statistic, which tells us how many standard errors away from 0 our sample is. We don't use that often. At least we're not going to in this class. And then it gives us a 95% confidence interval, which, can I go on a little rant for a second about p-values? So let's say you run a study and you find a p-value of 0.06. It's just outside the 95% confidence interval. So it's like, using standard measures of significance, 0.06 is not significant at a 5%, not 95% confidence level. If you run that study and you report that result to a journal, often your result will not be seen as important. It's like, it's not statistically significant, so we're not confident enough in that study. Some referees or journals will look at a 90% confidence interval. Let's say you run your study and you get a p-value of 0.11, which is just outside the level of significance for the 90% confidence interval. Your paper will generally not be accepted because it's not seen as significant enough, statistically significant enough. If your paper doesn't get published, that's not good for you. So there are strong incentives for you to change the structure of your study so that you can get a p-value that will get your paper reported in a journal. So what confidence intervals do is create incentives to play with the sort of the credibility behind the scenes of your analysis. So we actually have what's called the replication crisis, sort of a catastrophic term for papers being published but are not able to be replicated. Like, it only showed up once. Only one paper is able to do it, and when people try to show it again, they're unable to. And part of the problem is that we use confidence intervals. This is only part of the problem, but it's definitely one of them. That confidence intervals create incentives to be a little fishy with your analysis. Sort of like when you see a yellow light, you hit the gas pedal. You try to like gun through the light. I don't personally do that. Cars scare me. I mean, I've done it before, but not often. But we have similar incentives. When there's like a red light, when you have to get your p-value below a certain level, it leads to a lot of problems. So the better thing to do in most people's minds is to report the p-value. So I want you to be not thinking about confidence intervals. I want you to be thinking about the p-value. So we're going to spend really all of our time thinking about p-values, which are mathematically equivalent to t statistics. So we're going to focus on the p-value and not the t statistic, and we're not going to focus on the 95% confidence interval. Rant over. Okay, so this is the thing we're looking at, the p-value and the coefficient. Those are the two values that I care most about. All right, that took 3 minutes. Apologies for your time. P-values are the thing we're going to focus most on. All right, so this is nice. What we're going to do next is try to visualize the model. And this is not something you've seen code for before, so I'm just going to show you what to do here. Thankfully, Seaborn has what we call a reg plot, which is a regression plot. Regression is just sort of one of the terms we use for the general linear model. So we can copy this over. This is a reg plot. So we're going to include data equal to data. And then our y value will be life expectancy. And our x value will be log GDP per capita. If I run this, I get the scatter plot like we have from above, but I also have the regression line going through. This is nice for bivariate data like this. We'll do something a little more sophisticated later. A couple of problems with the default here is that it includes like that error bar. I think it's a little hard to interpret what that's saying. It's a 95% confidence interval around the model, given the sampling distribution. I think for our purposes, we don't want it on this slide. I think it leads to some confusion. So what I'm going to do is actually include confidence interval equal none. And if I run this, then it takes it away, which I think is the right way to visualize these models, just with the line. But I want to add visual contrast between the line and the data, so I've also included this thing at the end, which is just to turn the line red. Okay, and this looks nice. Almost as nice as the figures I have in the slides, which you love, by the way. Okay, so any questions about that? All right, so unfortunately we don't have enough time to really get through the rest of this. I'm gonna show you a couple of extra things pretty quickly. The first one is how we make predictions with these models. So the general linear model gives us a line, which if our model is correctly set up, will be through the average at any given point on the horizontal axis. We have an equation for this line. That's the model that we fit. So we can make predictions about where on average we would expect the wait times to be at any given time of the day. There's a lot of variability here, but we can make predictions about what we would expect on average. So if I were to say, what wait time would we expect at 100 minutes after open, all we'd have to do is go to the x value equal to 100 remember, this is an equation for a line. So we're going to go to the x value equal to 100. So we're going to plug 100 into this x. We draw a line from x equal 100 until it hits the model itself. And that gives us a vertical value, which in this case is equal to 54 minutes. Sorry, 5.4 minutes. So at 100 minutes after open, we can find the average wait time as predicted by the model. And we can do this with a computer. We can do this with a calculator. This is a great mini exam kind of question. Tell me, given this model, what the average wait time would be at 100 minutes. Should we do? We'll do the first one on screen, and then I will have you do the second one with a calculator. You ready? So all I do is plug 100 into this equation. We have the equation for the line here. We fit it by minimizing the sum of squared errors, or the mean squared error, and then got these parameter values. The intercept is 4.31, so that's 4.31 right about here. And then the slope, the rise of a run, is 0.011 times x. And then all we do is plug 100 into this equation to get 5 minutes and 5.4 minutes. So I'm going to pull up my calculator, and I'm going to plug in, I'm going to say 4.31. Too bad you can't see this on the screen. We can do it in a notebook. So this is not, we're going to actually do this with the life expectancy or life happiness next class. But we can plug in 4. So this is for wait times. 4.31 plus, so that's our intercept term, plus 0.011, which is from the slope. And then we multiply this by 100. And this will give us 5 minutes, 5.4 minutes. 5.41. Okay, any questions here? But you can also do that with a calculator. So exact same process. Okay. So that's what this is doing. We can make predictions with this model that give us the average wait time at any given point in the day. That's the power of these models. Okay, so you're going to do this. You're going to come up with the average predicted wait time at 200 minutes into the day. We'll take 30 seconds here. Remember how to use linear equations like this, and then find a number. Okay. What's the number? Do I not have it in the slides? Oh my goodness.
In the bottom.
Oh yeah, 6.541 if you want to be even more precise. Terrible slides, terrible figure. Okay, so we're going to do this. The last thing we're going to do here is make some predictions about GDP per capita. And then the last thing we're going to do, which we won't get to today, is interpret these values, which is a huge part of what we do. So here's some code. This will just give you the parameters from the model we just fit. So if you copy this over, you'll remember we fit the model up here and called it model, but we can just get the parameters themselves, b0 and b1, which is the intercept and the slope. And if you want to just look at these, you can just print them out. So b0, which is a negative value, and then b1, which is the slope. So we're going to talk about the slope, but it should match exactly the number we got up here. We have b1 and b0. From here, we can make any prediction we like. So I'm going to say my x value, let's say we want the x value to be equal to 3. So log GDP per capita equal to 3. And then we're just going to write down the equation for the line. B0 plus B1 times whatever the x is, which is going to give us our predicted y value. When I run this, I get a happiness level of 4.3. Okay, so this is nice. We're going to spend some time at the beginning of next class talking about these interpretations. And then this may sound boring, but is one of the bigger ideas in regression, which is working with our residuals. So those green lines, the errors with our data. We have to be actually pretty careful with these things when we run regressions. In your final project, you're going to tell me about your residuals. Next class, we're actually going to get into how to think about whether our model is set up correctly or not. So that's where we're going. Next class, homework is due on Tuesday at the end of the day. Thank you. I didn't feel like it was fair to ask you to turn it in tomorrow, so you get most of a week. And as always, if you need a bit of an extension, just let me know. Yeah. Have a nice weekend. Stay safe. Have a good time.